billions of smart devices in use. This has completely changed the mode of data generation. Every click, every like, literally every interaction we have with these devices constitutes a data point. Another interesting observation here is that these data generating devices have compute power. They can support some data processing locally. With this new mode of data generation comes changes to our relationship with and understanding of data. The generated data is personal and hence sensitive. The data is literally documenting our daily activities at a very close granularity, and this raises serious privacy concerns. To make matters worse, adversaries today are more powerful than ever, as is evident from the plethora of data breaches that we have seen in the past few years. One of the most recent ones is the cryptocurrency breach that happened last year, where attackers stole cryptocurrencies worth about $30 million. In the wake of such serious privacy breaches, government agencies around the world have formulated privacy regulations such as EU's GDPR and California's CCPA. These regulations make it legally obligatory for organizations to uphold data privacy. Now, parallel to the changes in data generation, the way we use and learn from the data has also changed. For this talk, I'm specifically interested in the task of learning a machine learning model from the data. So now a machine learning model has to be trained on this massively distributed data. For example, consider a setting where every iPhone user is basically a source of data, and Apple is interested in learning a model about emoji prediction for iMessenger on the joint dataset of all of its customers. An additional characteristic is that these datasets are constantly growing and evolving. Hence, the corresponding models have to be frequently updated. Further, as I just motivated, the training has to be privacy preserving. Thus, what we are seeing is that modern applications necessitate new learning paradigms. An upcoming answer to this challenge is federated learning. I am presuming that everybody here is already very familiar with this setting, so I'll just introduce it briefly here. Federated learning is a decentralized learning paradigm where multiple clients collaborate with the server to train a model. Referring back to our previous example, every iPhone owner is now a client, and the server is owned by Apple, who wants to train a model on the joint dataset. An important characteristic of federated learning is that each client's raw data is stored locally and never exchanged. In other words, there is no centralized data pooling. Instead, clients perform local computation and send in focused updates intended for immediate aggregation. These updates are typically the gradients of the parameters of the model computed over the local dataset. The server uses this aggregate update to train the model iteratively. Now, let's understand the threat model here. First, the central server, which is say Apple, is untrusted. So we need to ensure privacy of the client's inputs. It is important to note here that just decoupling the model training from central pooling is unfortunately not enough to ensure data privacy. Prior work has shown that attacks can infer sensitive information about the inputs using just the updates. A common solution for this is to perform a secure aggregation of the updates. This is essentially a cryptographic protocol where the individual updates are masked and only the final aggregate is revealed in the clear. Now, on the flip side, the clients can also be malicious. The distributed nature of federated learning makes it vulnerable to poisoning attacks. It is extremely easy for an adversary to inject a bunch of fake users who submit poisoned or malformed inputs to the server. This compromises the integrity of the training phase. These poisoning attacks can be either untargeted, where the goal is to reduce the overall accuracy of the model, or targeted, where backdoors for some target class is injected. These attacks can be quite severe. In some instances, even a single malformed update can significantly alter the trained model. Hence, to ensure robustness of the trained model, we need to check for the well-formedness of the inputs. That is, ensure input integrity. In other words, we should be able to detect syntactically incorrect inputs. This problem is especially challenging in the context of secure aggregation, since the individual updates are masked, thereby preventing direct audits on them. Thus, the ideal goal is to ensure both input privacy for the clients and input integrity to protect the global model from poisoning attacks. The problems of input privacy and integrity have been well explored, but only in isolation. Prior work that addressed both privacy and integrity is very limited and suffers from a host of drawbacks, such as support for only limited integrity checks, high computational overhead, or unrealistic threat models. To this end, I have proposed Eiffel, which is a cryptographic framework that supports arbitrary integrity checks without violating privacy. And this is the first general framework to do so. This is going to be the outline for the rest of my talk. I'll talk about Eiffel's design, followed by its workflow and evaluation highlights. I'll start with the problem formalization. In order to formalize the problem, first, we propose a new type of protocols for federated learning, which we call the Secure Aggregation with Verified Inputs, or SAVI protocols. Here, the server has a public validation predicate that defines a syntax for the inputs. An input U is considered valid and hence passes the integrity check if valid U evaluates to 1. Any per input robustness check from the machine learning literature can be a good candidate for this validation predicate. For example, the predicate could check that the norm of the input is bounded. Another example of the predicate could be checking the cosine similarity between the input and a clean update. In a nutshell, yes.
Sorry, Amrita, can I ask a quick question here? So
Sure.
just to make sure here, so you will not try to verify at all how U is computed, right? For example, by verifying the gradient computation or anything like that. You
No.
will verify here property of the
Yes.
update itself.
Yes. Yeah.
Okay. And here
Exactly.
the fact, in your second example, the fact that the check depends on 2 different inputs, that is, so it's not really only a function of U, I guess here, it's also a function of U prime. Where
so
U
the
prime
idea
might be,
is, so the idea is the server also has a clean data set and on which it can compute like a clean update. And then for this particular check, basically it's trying to see whether the cosine similarity between the clean update and the one that the client sent is sufficiently bounded.
I see. So it's not, you don't verify properties of pairs of inputs, right? It's only individual inputs that you...
Yes, individual. Yeah, we only verify the property of an individual input, but it could be with respect to a public clean update,
right,
but not across the secret inputs of multiple clients.
Okay, very clear. Thanks.
Okay, awesome. So in a nutshell, SAVI protocol securely verifies the integrity of each input and aggregates only the well-formed inputs. That is, the inputs for which we have valid U equals to 1. And only this final aggregate is then released to the server in the clear. Now, it is important to note that there is a fundamental difference between just detection of a malformed input versus detection and removal. With just detection, the server can only abort the current round of training, even when just a single malformed input is detected. This makes the server vulnerable to denial of service attacks, which renders it incapable of training. However, savvy protocols both detect and remove the malformed inputs, thereby allowing the server to train using just the valid updates. Eiffel is a system that instantiates a savvy protocol. Specifically, Eiffel can support arbitrary validation predicates that can be expressed as an arithmetic circuit with public parameters. An arithmetic circuit is a way of representing computation. It is very similar to a Boolean circuit, but instead of OR and NOT gets, we have addition and multiplication gets, and the computation is performed over a field. Eiffel does so in the fully malicious threat model. Specifically, this is the strongest cryptographic threat model. Here, the adversary constitutes a set of malicious clients and the server. The adversary is free to behave arbitrarily and can deviate from the protocol in any way they choose to. Moreover, they are also allowed to collude together in attacking the honest clients. Now, let us look at Eiffel's design goals. First, Eiffel should be flexible in terms of the integrity checks it supports. Second, Eiffel should be efficient. Finally, Eiffel should be compatible with the existing federated learning infrastructure in deployment. An important constraint here is that Eiffel should be able to work with a single server, which characterizes a realistic federated learning deployment setting. Now let's look at the building blocks needed for Eiffel. We use two cryptographic primitives here, secret shares and zero-knowledge proof. Secret shares is a multi-party computation technique which allows multiple untrusting parties to securely compute on their secret inputs. In this scheme, the secret or the private input is split into n shares, one for each party, such that any set of n-1 shares reveal no information about the secret. The parties can perform linear computation on the shares locally. For successful reconstruction of the secret, one needs access to all n shares. The second primitive is zero-knowledge proof, which describes an interaction between two parties, prover and verifier. The prover has a private input U and wants to prove some statement on it, such as in this case, the input is well-found. To do this, it sends a proof pi to the verifier, who decides on the validity of the statement by analyzing the proof. At the end of the protocol, the verifier is convinced of the proof only if the prover's claim was indeed true. Additionally, the verifier learns nothing else about the private input. In Eiffel, we use a specific type of zero-knowledge proof called secret shared non-interactive proof, or SNIP. SNIP is a lightweight zero-knowledge proof that is optimized for the client-server setting, where the client is the prover and the server is the verifier. It uses multiple honest verifiers for its protocol. The original deployment premise for SNIP, called PRIO, proposed to use multiple honest servers to act as the verifiers for the client prover. SNIP works on a private data U that is distributed using secret shares. Specifically, the verifiers hold shares of the prover's private value U and the proof pi. Additionally, the verifiers hold a public validation predicate, which is expressed as an arithmetic circuit. The goal of the verifier is to test if valid U holds without learning anything else about U. Yeah. Okay, so for this, the verifiers check the validity of the proof by gossiping among themselves. Specifically, they generate random digits T of their proof shares and accepts the proof only if these digests satisfy a certain condition, which in this case is that they sum to 0. Now I'll be discussing the key ideas behind Eiffel's design. For this, let's revisit the design goals of Eiffel. As I have just discussed, SNP supports arbitrary validation predicates in the form of an arithmetic circuit, so Eiffel is flexible. First goal, check. Now let's look at efficiency. Again, recall that SNP is a lightweight zero-knowledge proof that is specialized for the client-server setting. Hence, it is efficient. Also, here secret shares are used just for aggregation, which can be performed locally and is hence efficient. Second goal, checked too. However, when it comes to compatibility with existing federated learning infrastructure, we are faced with a problem. Recall that SNP requires multiple verifiers. Eiffel resolves this issue in the single server setting by making the clients act as the verifiers for each other under the supervision of the server. Specifically, when client I is trying to prove the validity of its input, all other clients J act as the verifier, and the server supervises the verification process. We are still not done here. The second issue is that SNP requires all the verifiers to be honest. However, as we have seen, Eiffel can have malicious clients and hence malicious verifiers. Eiffel tackles this challenge by extending SNP to the malicious setting by introducing redundancy in the verification process. Specifically, in Eiffel, we use a threshold secret sharing scheme, which is associated with a parameter threshold T. Here, any set of T-1 shares reveal no information about the secret. However, any set of T shares is now enough to reconstruct the secret. What this means is that any set of T clients can now emulate a SNP verification process, which results in redundancy. Any questions so far? Okay. So next, I'll be describing the workflow of Eiffel. First, I'll go over some notations and details of the problem setup. The number of clients in a single round is denoted by N, and M is the number of malicious clients. Here, the threshold T is set to be M+1. We also assume that every pair of clients have a common secret key. Additionally, every party has read-write access to a public bulletin board. In practice, the bulletin board can be implemented as an append-only log hosted at a public web address where every message and its sender is visible. Okay, so first, every client I splits its input and proof into N shares, one for every client. Next, it encrypts the shares with the corresponding common secret key and publishes the encrypted ciphertext on the public bulletin board. Now, client J decrypts its shares of client I's proof and input and computes its digest using SNP. Next, the server collects the digest from all the clients. Now, recall that since we use threshold cryptography, any set of T client is capable of emulating a SNP verification process. So the server now samples multiple T-sized cohorts and verifies the proof for each of the cohorts individually, which is basically summing the digest and checking whether they sum up to 0. The server can take the majority vote of all the outcomes and decide whether the proof is valid. The server then makes a note of all the clients with invalid proofs and publishes the list of such malicious clients. For instance, here, the server marks client I as malicious. Next, the server instructs the remaining clients to send in their share of aggregates, excluding the values corresponding to the malicious list. The server computes the final aggregation by taking a majority vote over the cohorts as before. What I just discussed actually gave a simplified and conceptual picture of Eiffel's workflow. Secret shares are very closely related to error correcting codes like Reed-Solomon codes. In the paper, we discuss a more principled approach for robust verification using Reed-Solomon codes and verifiable secret shares. We also present several performance optimizations.
So, Amrita,
Yes.
maybe quick question here. Maybe you're going to return to the so the server part that you just presented seems, at least the way you presented it here, to assume that the server is honest, which you assume it is not, right? So can you, maybe this is what you call robust.
Yes.
But maybe you can give a little bit, I don't know, unless you talk about that later, but otherwise perhaps you can give a little bit of
Yes, I do have some additional slides on this actually, which maybe I can talk about. So what I mean here is like server, so there are two goals, right? Input privacy and input integrity. The server is malicious for input privacy, but we consider the server to be honest for input integrity. And the reason is twofold here. So let's consider that even for input integrity, if we consider a malicious server, then the server can essentially do two things. One is it can mark the input of an honest client as invalid and exclude it from the aggregation. The second thing is it can mark the invalid inputs of a malicious client as valid and include them in the aggregate. These are the only two things they can do. Now, for case one, which is the server incorrectly marking the valid input of an honest client as invalid and excluding it, this is actually prevented in Eiffel. I did not talk about it here, but Savi protocols guarantees that all the aggregate will be containing the inputs from all honest clients. So this is a guarantee that Savi protocols give. So case one is prevented by Eiffel by definition.
I see. So this is using verifiable secret sharing?
Yes. Yeah. We ensure that all of the honest clients data that actually pass the check, all of them have to be included. That is guaranteed. Right. And for case two, which is the server kind of marking an invalid input as a malicious client, this actually is completely at odds with the server's goal, because the server's primary goal is to train an good model that satisfies input integrity. So this action goes completely against its main purpose, and hence it is kind of unnecessary to protect against a server for case two. Does this make sense?
Yes, it does. I guess this threat model may or may not apply maybe in some cases, right? But I can see where, yes, in some cases where the server is incentivized to get.
Yeah, so it's like the server here wants to train a model that is protected against poisoning attacks. So, I mean, an useless server, like a vacuous server could be like, even after doing all this process, the computing a good aggregate, the server is also like free to completely chuck that aggregate and take a junk aggregate and use that to train the model. Like in theory, a server could also do that, but that is kind of literally going against its goal, like against its incentive to train a good model.
Right, right. Although you could imagine maybe inserting backdoors that make the model still good, but maybe have some particular behavior that the server has interest in having or something like this. But I understand you. So you more or less exclude this here.
Yeah, I mean, yeah, here what we are assuming is that the goal of these backdoor attacks is to violate the model's integrity. That is why, since this is the goal of the attack, that is why this is completely against the server's incentives. And hence, this makes sense in our threat model, I believe. Does that answer your question?
Yes, it
Okay,
does.
awesome.
Thanks. Fair enough.
Okay, let me get back. Okay. So I think we went through the workflow of Eiffel, and now let's see why this is a savvy protocol. First, the privacy is ensured by setting the threshold appropriately. Recall that M is the number of malicious clients. So if we set the threshold T to be greater than M, which is say M plus 1, then clearly a collusion of M clients who have access to M secret shares cannot violate privacy. And now coming to the integrity constraint, it can be shown that the server returns the aggregate of only the well-formed inputs as long as the number of malicious clients is less than 1/3 of the total client size. Hence, to summarize, the core technical novelty of Eiffel is that it provides an efficient extension of the snip-proof system to a fully malicious threat model in a single server setting. Now, coming to the evaluation highlights of Eiffel, we evaluated it along 2 dimensions, accuracy and performance. Our evaluation uses 4 popular machine learning datasets, and our prototype implementation uses Shamir secret shares. We evaluate 6 poisoning attacks, ranging from the classic label flipping attack to the state-of-the-art strong attacks, such as min-max and min-sum attack, as well as backdoor attacks. To demonstrate the flexibility of Eiffel, we evaluated it on 4 validation predicates, such as checking the norm bound or cosine similarity. Recall that I mentioned that in the paper, we proposed a bunch of optimizations for improving the performance of Eiffel. For our accuracy experiments, we test whether these optimizations affect the efficacy of the validation predicates. We observe that Eiffel is able to match the training accuracy of that of the baselines that apply these validation predicates on the plain text. Coming to the performance of Eiffel, we observe that Eiffel has low computation cost. For instance, with 100 clients, out of which 10% are malicious, Eiffel trains a model on MNIST to the same accuracy as that of a non-poisoned one in just 2.4 seconds per iteration per client. The associated communication cost is also low. For instance, for the same example, the communication cost for client is 13.3 MB. Our proposed optimizations improve the performance by up to 2.3 times. We also evaluate Eiffel's performance improvement over a baseline prior work, BRIA. BRIA employs a different approach for robustness and implements a secure version of the multi-crumb protocol, which is a robust aggregation protocol that detects outliers based on pairwise distances of the inputs. Nevertheless, we chose BRIA as our baseline since it has the closest fit with Eiffel's functionality compared to other prior works. We observed that Eiffel is significantly better performant than BRIA. For instance, for MNIST with 250 clients, out of which 10% are malicious, Eiffel reduces the computation overhead by 18.5 times. Coming to the conclusions, I will discuss some future directions to explore. An interesting direction is to integrate Eiffel with differential privacy, which is currently the state-of-the-art de facto standard for achieving data privacy. So recall in secure aggregation, the aggregate is revealed in the clear. However, this aggregate itself can violate input privacy. So we need to release a noisy aggregate instead that satisfies differential privacy. the way we can extend this in Eiffel is as follows. So when the clients send in the shares of the aggregate after the proof verification stage, they can add shares of suitable noise, such as discrete Gaussian, to their share. Thus, the final aggregate computed by the server will be noisy, and this ensures differential privacy. The use of differential privacy here is actually win-win for us, since prior work has also shown that DP can also aid in robustness against poisoning attacks. Another direction is to improve the efficiency of Eiffel further. The dependence on N, which is the number of clients, can be improved to a logarithmic one by using techniques such as threshold homomorphic encryption. The intuitive idea is, instead of having each client verify the proofs of all others, we can make them verify the proofs of only around log n other clients. Another direction is to extend support for other types of integrity checks, such as the statistical tests like z-test, chi-square test, or ensuring that the data satisfies the correct functional dependencies. Thus, in summary, I have established why federated learning requires both input privacy and integrity, and discussed a system to achieve this called Eiffel. Eiffel enables a learner to employ arbitrary integrity checks on the individual inputs without violating their privacy. And Eiffel is performant and efficient even in the fully malicious threat model. Thank you for listening to me today, and I would be happy to answer any questions you may have.
Thanks a lot for the very nice talk. So I have a few more questions, but maybe we can check first with the audience if some people have questions. Please, you can raise your hand or just type in the chat. Maybe while people think about questions, I can maybe ask first one. So you talked a bit about efficiency, and also at the end you gave kind of these big O costs. So I guess those were to be understood as the per client cost, right?
No, yes, yeah.
So in particular with the scheme as you presented here, the communication cost is kind of order n per client, right? Because they need to communicate essentially.
It is actually the exact asymptotics are actually order of NMD. N is the number of clients, M is the number of malicious clients, and D is the dimension of your data, basically. So out of this, the dependence on the first N, that can be reduced to log N. That kind of comes from the fact that every client in the current prototype, every client actually verifies the proof for all other clients. Hence, that results in the linear dependency on the N. This can be reduced to log N by making the clients, instead of verifying it for every others, you can kind of construct K regular graphs where K is of the order of log N, and only you verify only your neighbors in that particular graph, communication graph, kinda. So in this way, then the reduction after that, the reduction would turn out to be like log N MD. That would be kind of the improved dependence.
This is based on the improved secure aggregation paper.
Yes, exactly. Yeah, right? The idea is similar to that. Yeah.
Great. Do we have some questions in the audience? Not. Apparently the talk was also very clear, which I think it was. So great. And then maybe I can ask more questions if you don't mind. Yeah, so maybe one is a bit on the maybe on the let's say the privacy and security analysis. So is it the case that here the security analysis is done at the level of a single round? So can you say something about what happens over multiple rounds?
I mean, you can treat each round to be independent. So, and they're like orthogonal. So every round as long as in every round, the number of malicious clients is bounded by less than 1/3 of the total client size. So we are ensured both privacy and integrity. And this is true for like this guarantee works orthogonally and independently for each round. So, I mean, it really won't affect if you continue this evaluation for across multiple rounds, if that makes sense.
Right. So the reason I ask this is because so this already potentially applies to just regular secure aggregation, but the rounds are not completely independent, right? Potentially, because the same clients may participate
Yeah.
in several rounds. So in
So
particular, if you do things like client subsampling, so there are a few papers, right, who recently, I don't know if you're aware of them, who showed that you can, in a way, you can attack secure aggregation in the case of federated learning because they are done over multiple rounds, and so you can try to reconstruct the average update of a client, for instance, which might be already sensitive, right? So this is why I'm asking about this. I guess this is a potential problem that is shared by your approach just because you rely on the security of secure aggregation, right?
Exactly. So I think what you are essentially, the assumption for secure aggregation is that anything that can be revealed from the aggregate is fair game. Like that is kind of beyond the scope of privacy, so to speak. So I believe the attacks that you're talking about that can be carried out just on the final aggregates. So if an adversary even just sees the aggregates across different iterations, they can, using these values, they can figure out some sensitive information about the clients. And currently, this is beyond the scope of secure aggregation. So for that, technically, I believe what I discussed, like a possible mitigation strategy would be to not just release the final aggregates, but release a noisy one using differential privacy. And that would give you some kind of formal guarantees. And of course, then the composition across different iterations also need to be taken into account.
Right.
Does that answer your question?
Not really, I guess. So what I had in mind is attacks that exploit the fact that you release several, because you do this for several rounds, you release several aggregate values that contain, some of them containing updates of the same client. And so there are recent attacks that use, so they're not trying to infer information about a single aggregate, but they exploit the redundancy in the participation to recover. You know, if you have a particular pattern of participating clients, you can, in a way, and you know who participated at which round, you can solve some kind of linear system to, for example, recover the aggregate update, but of a single client, which of course can be problematic much more than the aggregate update across different clients. So in this case, you can sometimes recover the aggregate update of a given client over the rounds, something like that.
So again, if I'm understanding it correctly, these attacks, the only information that these attacks need is, again, just the final aggregate, right? From across different rounds.
Yes, that, and usually they assume knowledge of participation, who participated.
Some auxiliary information. Yeah. Yes. So for secure aggregation, at least for the MPC version of it, any attack that can be carried out, any information that can be leaked just from the final aggregate is beyond the scope of privacy for us. So for us, the privacy is you cannot learn anything else apart from the final aggregate in a single round. But yeah, as you said, across multiple rounds, just by using this final aggregates across multiple rounds, you can still, and with some auxiliary information, you can still figure out the individual updates of the clients. This attack would still be possible in this case. And currently it's, yeah, beyond our scope.
Right. Which is makes perfect sense given the assumption that that you make. But
yeah, given that, yeah, our security goal is literally, the privacy goal is the same as that of secure aggregation. So anything you can do on secure aggregation, it also is applicable here, these attacks.
Right.
Yeah.
Right. And maybe I have a last question. So on the extension with differential privacy, maybe at a high level, like you explained, I mean, it seems maybe quite direct given these discrete kind of mechanisms. Maybe there is subtlety in how to scale the noise exactly, whether you can do better than scaling to the number of honest users or something like this. Can you elaborate a bit on that maybe?
I think, to my current understanding, the extension is straightforward in the sense that if all the clients kind of know what is the number of true, if they have a knowledge of the number of malicious clients, a maximum number of malicious clients, you can kind of take that into account in computing the parameters for the individual noise for the discrete Gaussian that you need to add. And accordingly, so that you make sure that if all n minus m clients add this amount of noise, make sure that n minus m clients add their required amount of noise so that the final guarantee still works up. So as long as you can have an assumption on the maximum number of clients, you can take that into account in computing the exact parameters.
Right. Yes. All right. Thanks a lot. Do we have questions in the audience? It looks like we don't. So again, yeah, a bit unusual time for the seminar. So I think a lot of people actually watch the talk offline and they won't be able to ask their questions. But you know, that's how it is. Yeah, there are not more questions. I want to thank you again for this talk. Very interesting work. And